Look, I'm just a geologist. I like rocks. I love rocks.
But speaking of mountains forming, I'm going to use this as a segue I want Bill to talk to us about the Himalayas.
The Himalayas,
the
yes.
Himalayas.
Yeah, so the paper I sent you guys, the Farnsworth et al. 2019 paper, it's really surrounding an interesting topic. It's not so much specifically about the Himalayas, it's about the monsoon systems that the Himalayas help to drive. And so why does anyone around the world care about Asian monsoon systems? Well, the food security for a third of the world's population depends on rains that only happen half the year. And then the other half of the year, some years it doesn't even rain in some locations, or it's just very, very dry. And most of the food you grow comes from, a 6-month interval of rain. And the Himalayas help to drive that. So there are these big scale questions, like these are global scale questions. What makes these seasonal turn on, turn off patterns of rainfall? And it all starts with the sun heating the earth, and that is what drives the Hadley cells. So that's evaporation off of the oceans going up and going poleward and then descending. And it's that the area where the evaporation's happening is where the water will condense and come back down. If you go poleward, where the air starts to descend back down, it doesn't have any raindrops with it. So it's descending dry air, and that's where we get desert belts. And so what's neat, though, is because the Earth is tilted on an axis, it goes around the sun, the place where the most insolation, the incoming solar radiation, happens, actually, from our perspective, migrates north and south throughout the year. It's always coming directly from the sun, but because we're tilted, part of the year, northern hemisphere gets it, the other part of the year, southern hemisphere gets it.
Our good friend, the seasons.
The seasons, there we are. But what this also drives is a belt of intense rainfall that tracks maximum insolation. And that migrates northward and causes monsoonal rains in places like southern India and the Malaysian Peninsula, Eastern Africa.
Isn't it, part of it's a function of it heats, it's heating the ocean more, and so the ocean is cool. It's like a relative land-ocean effect where the land heats up, say, faster than the water, so you're going to have this temperature gradient where the air is going to move from high temperature to low temperature, low pressure to high pressure, right? So during, I guess, the summer on land, the air mass is moving off land to the water. Is that right? And then
it's the opposite. The opposite.
Yeah.
You heat up the land more than the ocean, and so the air above the land goes up. The ocean air fills in that void,
and it's
bringing moisture.
And by the way, real quick, for those of you who are just listening to the podcast, you should see the magnitude of hand gestures that are going on right now.
I'm going to have to put this on YouTube
for these explanations. So please check out YouTube too for a full explanation on this.
It's an interesting. It's super interesting in sort of what you're doing and how you're thinking about it, sort of in the modern and trying to understand. Like, when did this start? When did the monsoon turn on?
Yeah.
And I know people have been trying to apply similar concepts to, like, the early uplift of the Appalachian Mountains and create sort of these, trying to say, was there a monsoon, over North America 100 million years ago or 200 million years ago?
And you can ask those because of basic questions. Like we see the process you were describing is called the sea breeze monsoon.
Ooh,
and
like
one of the questions in the Farnsworth paper was, okay, we have these Himalayas pop up. At what point does the monsoon system transition from the intertropical convergence zone, that migrating belt of rainfall driving rains, versus what you were describing with the sea breeze driving the rains. And how much of a mountain belt do you need? And does it matter if the mountains are there? And if you'd start answering those questions, all right, Appalachians get launched up. Was there a monsoon? The Rocky Mountains get launched up. Was there a monsoon? And you can, well, what latitude were they at? Those are the neat questions that it allows us geologists to dream up.
That's interesting. It's all, and like, does the rate of uplift matter, like to alter these air currents and so on and so forth?
I have a $1 million dumb question. Is the jet stream always going in the same direction because of this rotation of the planet?
Yeah.
Okay. I just wanted to make sure, it's always going from west to east, chasing its tail.
In the northern hemisphere.
Yeah, in the northern hemisphere. But so if you have mountains on the western edge of a continent, would you then get a monsoon in the northern hemisphere? Because that effect is now going over the ocean before it hits the land, as opposed to going over the land before it hits the ocean.
Yeah, and so you can essentially launch, it's a wonderful question. You can launch a large mountain belt up, and it will either create a huge rain shadow, or it can deflect the patterns of these winds. And so the Himalayas have done a great amount of deflecting seasonally of the latitude at which things like the jet stream occurs. The Sierra Nevada does it as well, and so there are people who studied the geochronology of the Sierra Nevada. When did the Sierra Nevada rise up? And then they'll match that with isotopic tracers of rainfall levels dispersed from sites all around, Eastern California. And you can start to answer questions like, all right, well, when the Sierras were a certain height, were we still seeing this pattern of a lot of rainfall coming over? And at what height did they get where we start to see signatures in the isotope signals that are saying, it's starting to dry out. Maybe this is deflecting rain patterns elsewhere.
Really cool.
Now, that's a very different thing than a monsoon system, but similar world. Yeah.
What types of isotopes would you use to look at that?
Go Topes.
Oxygen and hydrogen would be the most direct.
Yeah.
No. So sorry.
Oh, go ahead, Jesse. Yeah.
I was going to say, I feel like I've got this in the back of my head. Wasn't someone working on hydrogen isotopes, like looking at paleoaltimetry?
Totally. Yeah. There's one person I know of who does that is Michael Wren. He's in Connecticut. I think he's at UConn.
Yeah.
I think he's at UConn.
He is at UConn.
A friend of the podcast is working on his PhD with him right now.
Yep.
Nice.
Climbing up mountains, taking leaves, and looking at isotopes.
Yeah, there's a neat term for that. So when you climb up a mountain, you rain out the heavy isotopes. Yeah. So it's like having a bag of M&Ms where you have red and green M&Ms. If the red ones are the heavy ones, you start walking up the mountain and you're just dropping the heavy load as you're climbing up the mountain. So by the time you get to the top, you have all green M&Ms, and all the red ones are left behind down at lower elevations. And you can calculate that rate at which you're losing the heavy isotopes, and it's called a lapse rate.
Yeah, classic.
I mean, that's
M&M,
a classic geological
classic
problem, but
M&M lab.
I like.
It always goes back to that.
Yeah, I'm always like, if you're carrying a bag and it gets heavy, you're going up the stairs, you're going to start dropping the heavy stuff out of the bag because you're lazy.
Because you're lazy, because we're all lazy.
Yeah, nature is like me in that it wants to do very little work.
But then there's always that David.